So anybody who's not here is going to be able to catch it later. All right, so you don't have to write anything down here. This is stuff we've done already. And this is kind of was our conceptual starting point. The conceptual starting point was this idea that we can change the motion of objects. And that is sort of at the heart of most of what we're going to end up doing in physics this year. There's a couple other things that we'll look at, and not all of physics is purely concerned with changing the motion of objects, but a lot of it is. That's where it all started, right? It all started with this idea of, it started with warfare. It started with the idea of what do we need to do to make sure that this big rock hits that hut over there, or this, that's what it boiled down to. That's where all of this stuff started. And, from there, it's branched off into a bunch of things that are less disturbing and really incredibly useful, but much of it boils down to this idea of, well, how fast is something going? Or how can we change how fast something is going? What do we need to do to make that happen? And so our first big insight to that was with Newton's second law, which said, if we know that overall force acting on an object, the sum of all the individual forces acting on an object, that'll be equal to the object's mass times its acceleration. Which means, if we want to know how an object's motion is going to change, that's what acceleration is, then all we need to know is what forces are acting on it, including their sizes and directions, and how much mass does the object have. And that turns out that under the circumstances that we looked at it, it turned out to be really useful. What we did is we took carts and we hung masses off of a pulley. And then we were able to, with just not too many initial measurements, make predictions about how fast it was going to move or how quickly its speed would change, because we could evaluate all the forces acting on it. So that was pretty easy. But there's a couple problems with Newton's second law if you're not dealing with carts on a ramp being pulled by a weight hanging over a pulley. And the biggest issue is that it's really difficult to measure instantaneous forces in acceleration. By that I mean the force acting on an object over a very small period of time, and its resulting acceleration over a very small period of time. It's difficult because even with our sensors, if the force or the acceleration are changing, then as soon as we make a measurement, our force is different and our resulting acceleration is different. And so if we have a way of tracking an object's acceleration on an instantaneous basis, or looking at the forces acting on an object on an instantaneous basis, then this is relatively useful. But if we can't really do that, then it sort of all falls apart, because different forces result in different accelerations. So knowing something about the forces that were acting on something isn't all that useful if those forces aren't acting on that object later on. So that's why we had our setup, whatever we did, every time we were working with Newton's second law, it always involved the same basic, gravity was our force. Gravity was pushing things around, and that was it. Nothing else was involved, because anything else wouldn't have been a constant force. We can't really look at us throwing a ball. That's a really difficult thing to look at using Newton's second law, because the magnitude and the direction of the force acting on the ball are changing constantly. That ball leaves your hand and you're like, okay, well, how hard did I push on it? Who knows? It's really almost impossible to figure any of that stuff out. So unless we have constant forces, this isn't all that useful. So we used it when we had constant forces. But as soon as we switched to looking at forces that weren't constant, we looked at a completely different way of evaluating changes in motion. And that was by looking at momentum and impulse. And that's where we realized, okay, wait a second. If we look at the average force acting on an object, and we figure out how long that force is acting, then that'll tell us an object's change in momentum. And change in momentum has to do with mass and velocity, so we can figure out changes in speed by looking at that. And that worked really well for our carts bouncing off of each other because we knew there was going to be a constantly changing force. That spring isn't pushing at all until the carts come into contact. And then the force increases and increases and increases, and then it decreases and decreases and decreases and goes to zero. But we didn't care that the force was changing. All we needed was to be able to find the average force and then figure out how long that force was acting for. And we could get some good data and use that to make reasonable prediction. So those are easier quantities to measure, and they allow us to deal with constant forces, or with variable forces, so that's great. But it can be difficult to do this, and some of you may have noticed this actually with the carts. The carts work because of the nature of that system, but there was a fundamental thing that I think maybe some of you noticed. Even if you can't articulate it, I bet you all of you at some point thought, hey, wait. So think about the fact that these carts are like if you had to do this with a stopwatch, you'd never be able to pull it off, right? Like measuring how long those carts are in contact with each other would be impossible for you to do with a stopwatch, right? So what did we do? We used the computer. The computer has a super accurate clock. The timing of a computer is literally, I mean, these microprocessors work in gigahertz. That's billions of cycles per second, which means they can highly accurately time things down to a billionth of a second. That's great, except there was a problem. Did anybody notice anything weird about the times that they got in the impulsive collisions lab when we were bouncing the carts off of each other and looking at the force acting on one of the carts and the amount of time over which that force was acting? Did anybody notice anything unusual about those times? Yeah.
They were almost the same every time?
They were the same every time, and that seems a little bit weird, doesn't it? I mean, if you were to do the exact same collision over and over and over, that would make sense, but you didn't. Sometimes they rolled slower. That seems like that should have been a longer collision. Or maybe that should have been a longer collision. Or maybe if you have heavier masses on it, it seems like that should take longer. But it didn't. They all kind of took about the same amount of time. And the reason for that is because despite the fact that the computer itself has an incredibly accurate clock, the force sensor can only take so many measurements each second. So one of the things that was going on is that the force sensor can only take measurements 10 times a second, I think. So collisions that are shorter than about 1/10 of a second, we don't get any data for, or our times are all going to be 1/10 of a second. So this system doesn't work if we have trouble measuring really short-lived forces. So think about a baseball and a baseball bat, for example. If you're swinging a baseball bat, we could think about impulse, but how are you going to measure that? How are you going to measure the force, and how are you going to measure the amount of time? It's almost impossible to figure that out. So this ends up being clumsy because short times are really difficult to measure. The other thing that's a little bit interesting to think about here is that while it's frequent that we're going to have systems where forces start small, gradually grow larger, and then gradually grow smaller again, that's a reasonable thing to sort of try to engineer. It's not 100% certain. I mean, there's no reason that forces can't stay low for a while and then jump way up and then kind of hop down and then hop down and then hop down and then hop down. If you think, for example, about a vehicle, that's how forces look in a vehicle. You are at a stoplight, you're not moving. The light turns green, you hit the gas, that's a lot of force. Your car accelerates until you get up to whatever speed you want to get, and then you stop accelerating and you maintain that not acceleration for a while. When it comes time to slow down, maybe you do it quickly, maybe you do it slowly. Maybe you slow down from 45 to 35, and then a few seconds later from 35 to 25, and then come to a stop. Like, there isn't a predictable, like, bell-shaped curve that we would expect to see for the force of a car engine acting on the axles, or the force of the wheels acting on the road. So, both of these systems that we've used have their place, but they're not perfect. So we have another system that we can use to think about the change in motion of an object, acceleration basically. And that has to do with forces and distances. And here's the logic behind it, all right? So it seems weird to think about, well, like, how do you know that we can use the distance an object moves to infer anything about how its speed is changing? But actually, it turns out it's not that difficult to grasp. It starts with the idea that time has to pass for an object's motion to change. You can't have motion change if no time goes by at all. And if motion is changing, an object has to move. If it's already moving, then it'll either speed up or slow down, but either way it's going to move as it does that. So there's some distance that it moves. Even if it's not moving, like at one time, if it's not moving, in order for it to change its velocity, it has to start moving. Or even if it ends up motionless, in order for it to end up motionless and still have its velocity change, it must have been moving at first, so that it slows down and stops. So no matter what you look at, any object that has changing velocity will move. It has to move. As its velocity is changing, it's going to speed up or slow down or change direction, but it has to move while it does that. So that means that any time forces are affecting the motion of an object over some period of time, it's gonna move. So maybe we can use that instead. So if you think about time, like time is really difficult to measure, but distance isn't. Even real small distances aren't that hard to measure. If something moves like a millimeter, we can see that, we can measure it more easily than if something like is experiencing a force for a millisecond. Like that would be impossible to measure, but measuring an object's motion over centimeters and millimeters is pretty easy. So what we're gonna do is we're gonna look at this idea of force as it pushes on a moving object. That's gonna be the key, because if we can nail down some connection between the amount of force that's being applied, the distance an object moves, and the resulting change in velocity, then we have a system that's going to allow us to make some pretty robust predictions. And that's where we're gonna land starting tomorrow and really diving in on Thursday, making predictions about how an object's motion will change. But it starts with thinking about springs. So what I'm going to ask you all to do is think about how you could predict how much force a spring is exerting by thinking about how far it's been squished or stretched. And it turns out it's pretty easy to make the measurements that we need. I'll show you how to do it in a second. But if you think about a spring like this, imagine if you start pulling it, at first it's not pulling very strong, but the more you pull it, the stronger it pulls, right? And if you squish it, the same thing happens. The more you squish it, the more it pushes. And it's predictable. Like if I pull it out this far, I can feel it pulling back on me. If I pull it out that far again, it's the same force. Squishing is the same way. It always takes the same amount of force to squish a spring a certain amount. So the force exerted by a spring is predictable, and it depends on how far it's stretched or squished. So what we want to try to do today is figure out what the connection is between the distance that we squish a spring and the amount of force that it is exerting. And then ultimately what we're going to do is think about, okay, well, if we can figure that out, if we can figure out force and distance, then maybe we can use that information to think about what if we use a spring to change an object's velocity. The system we're gonna use is our supercarts, because it's gonna make a lot of the measurements really easy. The supercarts have a spring on them, and that spring pushes on stuff. So if I push a little bit and it squishes a little bit, I can feel it pushing back a little bit. The more I push, the more I can feel that spring pushing back. We have a really easy way to measure the amount of force that is being exerted by the spring, and I'm not gonna show you the details of this right now, but you could probably figure this out. If you take a supercart and you put it, doesn't have to be on a track, just on any surface, and you have the force sensor on one side and the spring on the other side. If you take that supercart and you push it up against something, and you measure the force on the force sensor, then Newton's third law and some free body diagrams will demonstrate that the amount of force that the spring is pushing on your finger has to be exactly the same as the amount of force that's being recorded by the force sensor. So in other words, if we have a cart like this, and we have a spring like this, and a force sensor on the other end, then this force right here, and this force, the force of the spring, are gonna have the same magnitude. Okay, as long as it's motionless and horizontal. Okay, so if the acceleration is 0 and it's horizontal, and you gotta make sure that you've zeroed the force sensor properly, because if you don't zero the force sensor, then this is still true, but the number that you get isn't gonna accurately represent the actual force that the force sensor is exerting. But this allows us to make really easy measurements of force. And then you can make really easy measurements of distance by just having a ruler kind of held up. And I mean, there's a couple different ways you could do it. I would probably just put the ruler under the spring, so that right now under the plunger, the plunger is right at 2 centimeters on this ruler, and then when I squish it down, I can squish it to like 1 centimeter or 1.5 centimeters. So I can get really accurate measurements of displacement just by eyeballing it, the distance, and I can get really good measurements of the force that that spring is exerting by using the built-in force sensor. And you can imagine, I hope, that when there's nothing pushing on the spring, there's also nothing pushing on the force sensor. So we know that if the spring isn't squished, the amount of force is going to be 0 as well. But if you collect more data here, you should start to see that as you squish it, the force goes up. And it's going to be in a predictable way, which means what you should expect to see is something like this. If you graph the distance you squish it against the force that the spring is pushing, as indicated by the force sensor on the supercart, you should expect to see that it's going to follow some sort of a pattern. Maybe it's like this, right? Like this would be indicative of a force sensor that, like, as it squishes, the force increases, but less and less and less over time. There are a couple of things that you have to watch out for. One is, as I said before, you've got to zero the force sensor. The other is that this only works when the spring is completely free to push. So that gets it gets a little weird when, for example, if I push enough to make the spring click in and lock, now I'm just barely touching the spring, but it's all the way in. So if I were to measure the displacement here, it's not giving me any indication of how hard the spring is pushing, because the spring isn't pushing on my finger. The spring is pushing on the little latch thing. And the other thing is, if you push the spring to the point that it doesn't move anymore, and then you just keep pushing, you can push harder and harder and harder and harder, but now it's not the spring pushing back on you, it's the whole cart pushing back on you. So you basically, this only works while you're kind of moving the spring within this relatively narrow band. It's about 3 centimeters that it can move. If you have a spring that's really sticky, then it's not gonna work as well either. And you can kind of play around with it. If you hear too much squeaking, or you can actually feel it like actively like grabbing, then we could put a little bit of like the WD-40 on there to loosen it up. But ultimately, what we're gonna be able to do is use that information to make predictions about how this spring can change the motion of the cart. And it makes sense, right? Like, something about the spring is making the cart accelerate. To change the motion of the cart, we have to exert forces. So it's the force from the spring is doing something. If we can figure out something about how that force changes as the spring expands or gets squished, then maybe we can use that to make some predictions about how fast it's going to be going. So your job today is to work in groups to collect as much accurate data as possible so that you can come up. The graph may not look like this. This was an example of theoretically what you could see, but this isn't probably what you are going to see. So your goal is to try to figure out what is the relationship mathematically between the force your spring exerts and the deflection, which is the distance that it's squished. All right? So that's your job. Does anybody have any questions before we get started? Okay. You should be able to get all your data collected and make a graph today. I'll let you know when you should start making a graph if you haven't already.